tell that okay, I have achieved this much, this is good enough. There is no good enough. You have to do as low as reasonable, achievable. Okay, so that's the goal. The International Commission on Radiation Protection tells that there should be a justification why somebody should be exposed to radiation. Without any justification, nobody should be exposed to radiation. You take an airplane, high altitude flying, and you have a justification because you want to fly, you will get some radiation. Okay, so that's how best to use resources in reducing the radiation risk to individuals and populations. Methods for dealing with optimize there are many ways you can reduce the radiation to the public. So that's what you should know, that what are the optimum way of reducing the dose to public. They range from simple common sense to complex techniques such as cost benefit analysis. Sometimes you can reduce the dose to a very low level, but at a very high.
You have to see that what cost benefit, how much money I am spending, what benefit I am getting. Exposure of individuals resulting from a combination of all relevant practices should be subject to dose limits or to the some controlled risk in case of potential exposure. These are aimed at ensuring that no individual is subject to radiation risk deemed to be unacceptable. Limits provide a clearly defined boundary of individual risk for application of the more subjective procedures of justification and optimization. Sometimes people tell that how I know that this doesn't harm me. I have been doing it for many years. That is not the standard practice. Standard practice is to follow an established guideline, and that established guideline is available from many regulatory agencies. So you should know that what are the limits of exposure to whom from where. Protection of patient, personnel and public as low as reasonable achievable. The recommended dose limits are available and regulated. National Commission of Radiation Protection provides guideline in USA. You have ABR, it's original for ARB, Atomic Review Board, enforced by state of Texas where I live. But here ARB is enforcing that, those things. So these are some of the dose limits that is available from NCRP report. I have not looked at ABR with the ARB report. Public 100 milligram, 2 milligram per hour for unrestricted area where anybody can go. Occupational workers like me, therapists, all kinds of things, those who are radiation workers. For them is 5,000 milligram, 5 grams. Pregnant workers 500 milligram, 500 milligram is 0.5 gram. Children under 18 years 0.1 gram or 100 milligram. Embryo or fetus, these are the limits, and that are also a sub-limit. Okay. This is monitored by many means. You can have OSLD, you can have a PLD, all kinds of things. You can have a neutron. You work at proton center. In the beginning, we had some 50% which can measure the neutron dose. There are some special PLDs which can also measure the dose. Okay. So it depends on what kind of exposure you are likely to receive. Sources of radiation hazard and proton therapy facility. What are the sources that people can be exposed to radiation and proton therapy facility? Uninterrupted exposure to primary proton beam. Suppose somebody was doing work. Two people were working together, and suddenly one of them exits out of the room, closes the door, and turns the beam on, without looking at what happened to the other person. So other person gets uninterrupted exposure. That has been prevented. how do we prevent that? That we have an interlock. Because there are many places where any person can be working without knowing his working. There is a big pit in which the gantry is, the gantry, house the gantry, the whole machine. Sometimes they go down, look at some electronics and all kinds of things they may be working there. So there are the intervals. That if somebody is in the pit, the door to the pit is open, then you cannot turn on the pit, the interval. So similarly, in the room where the patient is treated, when they are ready to treat the patient, there is a room search button. You press it. It sounds it rings a bell. So that the people who are inside, they will know that okay, radiation is coming. And then outside, that the radiation proton beam is ready, proton irradiation is going on, so that people cannot unintentionally open the door. So those are the safety precautions are taken at the proton center, not anybody to get unintentionally exposed. Okay. But these things are not available in standard Linux. Sometimes this can happen. People can hide somewhere, all kinds of things without knowing it. Come in a hurry, close the door, start the beam. You should avoid that. One of the principles of protecting yourself, somebody doing that to you, always take the key. The control key with you, so that you can do it. That's right. Exposure from secondary radiation. We say protons are nuclear particles. They heat something in the nozzle. Because nozzle itself has some primary blocking, primary apertures, big apertures to stop any radiation going around. Primary radiation. So those protons, specifically in scanning beam, that's not a possibility. Scanning beams are very narrow, so they don't heat many of these the nozzle components that much. But when you have a broad beam coming out, the possibility that the bead size can be 40 by 40, and that's why you have a primary aperture to block the beam to that level. But with scanning beam, there is the possibility of something hitting the nozzle components is very low. Exposure. So what happens when proton beam, when you are irradiating the patient, when it hits anything, then there is a nuclear reaction. Proton is a nuclear particle. There is a nuclear reaction, and it gets activated. Then some of the atoms may be excited. Nucleus get excited. When the nucleus get excited. Once the nucleus get excited, it will go to ground state. And when it goes to ground state, whatever excitement energy given by the protons, they are emitted as gamma rays. And they may also create some neutron trans. Neutrons will come out. That is one of the source of neutron in proton beams. What else? The X-rays will also come out, that interaction with atomic electrons. The X-rays will come out, gamma rays will come out, neutron will come out. So there are many secondary particles, there is secondary radiation that will come out. And then the activation stays for some time. It is not going down to zero immediately after the beam stops. They have lifetime. Every radiation activation has a lifetime. So during that lifetime, you will get also some residual exposure. Yeah.
Will this residual exposure accumulate over a period of every day on off?
There are some long-living isotopes that may be created, and they will stay active for long. Suppose you use the brass aperture. Suppose you have brass aperture has lead and all kinds of elements. Their activation will still come. So what happens? That's why the room where they are stored, there is a ambient exposure that's possible. Anybody who goes there, unnecessarily. So that's why we try to restrict people to spend too much time in that place. And after the patients are treated, those devices are moved to a storage area where they are allowed to naturally decay. And they are not released until the radiation level reaches to the acceptable limit. So, but now with scanning beam, you are not using that many apertures, so nothing will happen. that situation doesn't arise anymore. But you have energy absorption, but energy absorption is a low G magnitude. So the activation is not that high. So that's why the residual radiation level in the scanning room is high. And of course, all the workers that who go to the room, they carry the radiation tag. They always are required to have a radiation tag. So we monitor. Within this sitting photosynthesis center where I work, it is operational for almost 20 years. Within these 20 years, we have not seen anybody's radiation exposure which is above the tolerance limit. Okay, the radiation physicists, they get the highest exposure because we work on QA, we do water tank scans, 8 hours, 10 hours per day, and all kinds of things. And the water in the water tank gets activated. And if you increase photons, after you irradiate the water tank for a long time, you put your finger there, you will still get the radiation. There are some positrons, all kinds of things, and you will feel the skin reaction. Okay? So those are physicists, they normally get a lot of radiation exposure, but still they stay with it. I have not seen anybody gone out. That answers your question. Primary photon, photon, cyclotron, beamline, and equipment. This gives high dose to exposed personnel because on those rooms there are a lot of magnets and a lot of kind of hygiene materials. So normally that access to that room is very controlled. Nobody can go to the accelerator room easy. It's always locked. Only required personnel will go. Okay? If high dose to exposed personnel usually confined to highly sedated control area with a multiple introduction. That's how you can get some people staying there getting exposed, but we avoid this kind of situation by all means. Okay? It is prevented. Neutron and gamma radiation produced by the internal primary material in the feedback. I have already talked about it. Can give up to 10% of those primary exposed persons. So this from secondary radiation, neutron and gamma radiation, they can give those up to 10% of those primary exposed persons. The patient is irradiated. The proton beam goes inside. There are some hygiene materials, calcium, bone, all kinds of things. So the patient's body also gets activated. So that's why PET scanner works. You can put a PET scanner and use it to monitor where you give the proton. Because there are PET activators inside the body. They emit positrons, and there is positron electron annihilation happens. Then you can detect the gamma value by the PET scan. So that PET scanner has a lot of potential to do in vivo dose monitor. Safety system gates to separate zones is important. Interlock only short zones where interlock is only short zones. This is a picture of the cyclotron room in University of Pennsylvania. So they have designed different zones, and if anything is open, there are interlocks, and there are short zones. Happening is every zone is short. Every zone is short that nobody is staying in those zones. About 28 mR per hour, neutrons about 100 milligrams per hour. Unfortunately, no sensitivity data, but for sensitivity data, this is about 110 to 130 of passing. This data is from passing beam. No data, I don't have data for scanning beam, but it's about 110 to 130. Linear vault, as you can see, comparing the linear vault and a different room, this is pretty high, neutron and the proton. So that's why linear vault is very well protected from other people to get exposed. Radiation levels after 10 minutes of irradiation treatment, 1 meter per second. So 0 minutes after 3 mR per hour, 10 minutes this is the down very fast. So this is about what remains, 20 minutes. But it's very small here, 2 ml per hour, and nobody is going to spend 1 hour there. So I always instruct the physicist and therapist. After the beam is stopped, don't rush into it. Give a couple of minutes. Let the activity die down and all kinds of things. And this is for passive beam. In the passive scattering beam, you have aperture, you have compensator, all kinds of things. So the radiation level is high. But scanning beam, one of the reasons why the scanning beam is very much attractive is that the radiation exposure is and the neutron dose is very low. But despite this, as I told you, that none of the personnel who work at the coaching center have ever, their reading never came up with radiation exposure more than the dollars. If somebody gets more dose than the control, then what happens? They will get the call from the radiation protection officer and they will find out, did you do your did you put a tag inside the room by mistake? Because that happens. Sometimes the gas falls up and it gets exposed to the full radiation and their reading is high. So anytime that happens, you better report to the radiation protection officer. Okay? So that way they will know that okay, this is an accident that happened. This is the vault that they will remain high. It takes a long time. This is the radiation go down. I have already told you the radiation protection approaches, basic protection is time. Less time is less dose, distance, maintain distance, inverse square helps you, inverse square protects you, and shielding, reduce dose by activation by radiation dose by improving material, do the shielding of our things, all kinds of things. But the neutrons you cannot protect this. Neutrons only can be slowed down by hydrogen or hydrogenation. So that's why the secondary the neutrons that are produced by photon beam on those rooms, they have long mazes, and the wall is completely with a very concrete hydrogen material. So that way, around the maze, they will have multiple scattering and eventually hit the maze multiple times. So outside the room, the neutron dose will be meaningful. And of course you have to have a door. If you have a long maze, the door doesn't have to be that thick. If the maze is short, then you have to have a thick wall to protect anybody standing outside the room. Outside near the door. Radiation shielding principle is the same whether you are doing a X-ray room or a proton room or a electron, everything. So that the wall is protected. Those walls are designed for worst case scenario. And then the shielding calculations have become very standardized. Softwares are available. There are people who are very, there are whole professionals to design the shielding. Okay? So rather, a physicist always checks the shielding, but normally the shielding calculation for these expensive places is done by a professional whose only job is to do the shielding calculation because he is very skilled with that task. Many aspects of shielding are similar to the MBA X-ray microscope. The primary beam dose, workload, occupation constants factor, use factor to beam orientation and another primary leakage and scatter radiation. Those of you who are in the graduate physics programs in medical physics, they will study this because that's a required course of knowing the radiation, shielding, radiation protection, and all. Major concern of shielding design in proton particular facility is the secondary neutron. Neutron equivalent those weight factors in 20 for 1 mm, average weight factor 7 for proton therapy produce. Special consideration for secondary neutron. Difficult to determine the exact amount. This is usually estimated by analytical modeling facility and its machine specific. Most common shielding used to alternate secondary neutron are arc, concrete and steel. Steel has the advantage of being high density, creating thinner shielding. However, it also creates low energy neutrons and hence requires secondary shielding with concrete. Concrete has a lot of water, lot of hydrogen. So So that's why you can shield the neutrons very well. Large measures awareness help to reduce the neutron negativity and particle interaction with the hyper flows. I have already discussed. Let's keep this. We have the shielding design how to express. The neutron skyline. If you don't have a proper shielding, neutrons can escape from the room and they will interact with the cloud and they will provide some radiation somewhere else. So that's why it is very important that you have to not only measure your radiation level just at the top of the roof, but you have to measure at a distance, some distances from the roof to make sure your skyline radiation leakage is not affecting public. Okay? The neutrons can also activate the air inside your facility. So you have to be very careful that multiple this argon produced from neutrons at the reaction with copy argon. These argons, radioactive argon emit 1.3 gamma with half-life of 1.8 hours, can provide some exposure. This needs to be evaluated to ensure that concentration remains lower than the permission level. So you have to take your air sample, have a radiation activity level evaluated and make sure they are good, they are within the limit. Thank you so much, Sanjay. Okay, these are devices in passive spectrum. They can be activated as I mentioned. So this device gets very hot. Hot means it is activated emitters. So basically, the therapists who used to treat in passive spectrum beam, they have to change this very frequently. Okay, so that's why in the beginning we gave them the ring monitor. So this is what we used to do. Fingers. We also use that one to monitor our growth. But after many years we found that it's not so. So that's why we no longer use it. And this I have already talked about how the activation and compensation can be activated. Compensator is a low G factor. If this activation is not very high, but this can be very highly activated. So that's why it is normally after the treatment taken and put in the storage room for this. Interlocks and the monitor should prevent the accidental exposure. Primary and secondary dose monitor, beam level monitor, room sector interlock, door interlock, and a radiation level monitor. In every proton facility, you will see there is a gamma detector to know the gamma exposure or X-ray exposure, and there is also a neutron detector. Okay? So that you know what is the neutron dose surrounding the room. Warning labels. Warning signs about a high radiation level. This is required. You have to put in the door that where the radiation is taking place or where the levels can be high. This is required to put those signs so that people will be aware that you should not go there without checking with the facilities, the technicians or physicists who have a control over restricting people to that. So in our place, your badge, the only people who are supposed to go somewhere, their badge is activated to go there. Nobody can go. Okay, so that's why you prevent any patient even walk there. They cannot walk there. Somebody has to come and escort to that treatment. So that way they don't get unintentional escort. They come and stay somewhere else. Visitors come and stay somewhere else. They don't go to the high radiation area. Access restriction, that's the last thing. The routine procedure and complex state regulation that you have to do. Safety intervals to prevent accidental access to basically your beam should be terminating whenever it is supposed to terminate. So if you have to terminate the beam, those beam abort, beam pause button, they should be working properly. And of course you have to have dosimetry application like proper beam calibration, commissioning, this is part of the radiation protection also. You don't want to expose the patient or irradiate the patient with the wrong dose. That is also radiation protection. Ensuring that devices like pacemaker are not exposed to beam training of all possible involved in treatment. They should have some idea about radiation protection. They have, because they are all trained professionals, licensed professionals. It's required for them to know. Radiation protection is pretty good. Otherwise, the diagnostics, minimize the time of exposure is very important. Okay, that ends my formal presentation. You can now turn off.